afternoon, everybody. We are Spacecraft Preliminary Design. My name is Julio Benavides, the course instructor. And today we'll be presenting the PDRs for our projects. Because of our time constraints, we're looking it would be more of a summary of a PDR. But we'll be able to discuss any information, any details that you'd like during the Q&A section. We'd like to thank our panelists for coming in, taking the time to come in and observe our presentations, and I'll give them an opportunity to introduce themselves.
All right, so my name is Connor Warren. I'm an aerospace engineer, trained under Julio Benavides, AstroTrack as well. I currently do flight test engineering and some rocket propulsion, and I graduated in 2015.
Good afternoon. My name is Scott Blue. I'm retired military. Was in the military for 23 years. Worked on military classified space programs for the whole time. Since then, I've been involved as a contractor, consultant, working on exactly the same programs I was working on when I was in the military. So I've been here, now this is about the third year I've been coming to these presentations, so it's an honor to be here.
Hi, my name is Gentilini. I'm a professor here. I'm a colleague and very good friend of Dr. Benavides, and my expertise is robotics.
Hello, my name is Sophie Deskin. I am an aerospace engineer with AstroTrack, graduated in 2015, and right now I'm working at Northrop Grumman. I'm a flight test and lab instrumentation engineer.
I'm Patrick Deskin. Was a graduate from Embry-Riddle in December 2015. Currently a modeling and simulation engineer working with Northrop Grumman.
Thank you. And before we begin, I'd like to introduce our co-instructor, Dr. Patrick McElwain, our department chair, Dr. Mark Sensmeyer, and our associate department chair, Dr. David Lennon. And without further ado, I'll pass it on to Steph Fortes, who's going to talk about APOPHIS.
Thank you, Dr. Benavides. Good afternoon. This is the preliminary design review for APOPHIS, the automated platform for Overland Payload Haul and Import System. I'm Estelle Fortes, the project manager. In this presentation, we will discuss our mission concept, our system definition. We will discuss in detail each of our subsystems, their definitions and numerical validations. We will then move into our system numerical validation and finish with programmatics. APOPHIS is broken into 4 subsystems. Each subsystem has one technical team lead. The first subsystem is the structures subsystem, led by our assistant project manager, Karina Rodabach. Our propulsion subsystem is led by Sean Gilman. Our guidance, navigation, and control subsystem is led by Abigail Kudo. And finally, our command subsystem is led by Brandon Kleckman. Now I will discuss the mission concept. APOPHIS will be an autonomous land and air-based payload delivery platform capable of transporting a 5-kilogram payload to a user-defined target position. APOPHIS will also be able to detect and maneuver around obstacles that are less than 10 meters in length in the horizontal or vertical directions. Shown here is our CATIA rendering in addition to our 2-scale mock-up here. Now I will discuss our system objectives. Primary system objectives are defined as objectives that are required for mission success. That is to say that if these objectives are not satisfied, this will constitute mission failure. The first states that the platform should travel both on land and air to a target location. The second and third objectives state that the platform should deliver a 5-kilogram payload to a target location and then return to the starting location without the payload. The fourth and fifth objectives state that the platform should travel a distance that is greater than 50 meters, but less than 100 meters from the starting location. The sixth primary objective states that the mission should have more than one form of independent propulsion, in addition to more than one method of attitude determination and control. The ninth primary objective states that the platform should complete the mission inside the mission envelope. Now moving on to our secondary system objectives. These objectives are defined as expected but not required for mission success. The first 2 state that the platform should be able to maneuver around obstacles that are less than 10 meters in length in the horizontal or vertical directions. The third states that the platform should achieve an altitude that is less than 25 meters during the course of the mission. Now moving on to our tertiary objectives. Now these objectives are defined as desired but not required for mission success. The first states that the platform should complete the mission in full autonomous mode, and the second is that the platform should be fully validated by April 28, 2017. This is the date of our system validation review. Now moving into our concept of operations. As mentioned, APOPHIS is broken into 4 subsystems. First, the structure subsystem includes the body, the payload, and the payload bay. To initiate the mission, first, the platform is powered on. Next, the onboard computer establishes a radio connection with the ground station. And next, the onboard computer obtains a GPS signal. At this point in the pre-mission phase, the user is then able to define the target location at which to deliver and deploy the payload. This is done at the ground station. These steps are done within the command subsystem. Using the user-defined target position, the GNC subsystem, Guidance Navigation Control subsystem, will then calculate its trajectory. GNC is also responsible for detecting and updating this trajectory when obstacles are present. Propulsion will then execute this trajectory using either the aerial propulsion or terrestrial propulsion. With the successful completion of these steps, APOPHIS will be fully operational. And now here is an animation. This animation shows 2 types of obstacles that APOPHIS will be able to maneuver around. The first is an obstacle that is less than 10 meters in the horizontal direction, but more than 10 meters in the vertical direction, and he's shown here. And the second obstacle is greater than 10 meters in the horizontal direction, but less than 10 meters in height, shown there. So the animation begins with APOPHIS leaving the starting location. As it approaches the first obstacle, it will detect it when it is perpendicular to it, turn to maneuver around the obstacle. Once it is around the obstacle, it will return to the center position to continue on its trajectory. As it approaches the second obstacle, now switching views to see behind the obstacle, it will turn one direction, travel 10 meters. At that point, it will still detect the obstacle, so then it will return to the middle position where it first sensed the obstacle, travels 10 meters in the opposite direction. And at that point, it will still sense the obstacle, so then it will return to the center position where it first sensed the obstacle and fly over the obstacle to continue to the target position at which it will deploy the payload and then maneuver back to the starting location using an optimal route. I'd like to introduce Corinne Rodabat to discuss the system definition.
Thank you, Estelle. I am Corinne Rodabat. I will be discussing the system definition. First off, I would like to introduce my integration team. With me, I have Jessica Chow, Kaylin Hubner, and Joseph Prospero. So once again, this is the overview of our CATIA model, but I will be referencing to our mock-up. So first is the propulsion subsystem. Propulsion is first because it really is what drove our design. So we have 4 aerial motors, including counter-rotating propellers connected on top. These are located at the end of each propeller strut. And the terrestrial component is the ground motors, which are located in the front to give us front wheel drive, along with differential steering underneath the platform. The back wheels are freely rotating wheels to allow us to turn. Next is GNC. GNC is in charge of attitude determination, attitude control, and guidance and obstacle detection. So for attitude determination, they have an IMU that is located right here on the electronics panel in the center of the plate, and a solar panel array located on top of the batteries, so that way there will not be shadows cast on it, which will give us a sun vector. For control, they would just be using propulsion's motors, so the air motors for aerial control and the ground motors for ground control. And for obstacle detection, we have 4 ultrasonic sensors, one located at the end of each propeller strut. And for guidance, we have a GPS located in the central electronics board. Command is in charge of powering the system, data processing, and communicating with the ground station. They power the systems using 4 batteries located here in the middle of the plate. For data processing, they use a microcontroller located here. And for communicating with the ground station, they have a radio located here next to the solar array. They also are in charge, have electronic speed controllers to regulate the voltage that goes to our air motors to ensure we get the correct amount of thrust. Last is the structures. Structures is in charge of containing all the other systems. It has four main components, well, four-ish main components. We have the main plate and the propeller struts, which are both made of carbon fiber. We have the wheel chassis and the payload struts, which are located underneath the platform that are made out of aluminum, 6061. We are also in charge of the payload and deploying the payload bay. This is done with solenoids located on the payload struts that are hooked into a payload bay that will release when we get to our target location. All of this will be discussed in more detail within the individual subsystems. At this time, I would like to introduce Sean Gilman for the propulsion subsystem.
Thank you, Corinne. I'm Sean Gilman, and I'm going to talk about the propulsion subsystem. So with me on my team is Eli Olson, Joseph Prosper, and Wesley Stein. Now I'll talk about the propulsion subsystem definition. So, first two requirements is that the propulsion subsystem must move the platform with the payload more than 50 meters but less than 100 meters from the starting position. Next is that it must be able to translate at least 10 meters out of its expected course, either horizontally or vertically. This is to avoid any obstacles. And it must be able to keep the platform under 25 meters above the ground level throughout the entire mission. Next, we have the propulsion subsystem must provide 27 kilogram force of thrust. This is to account for a factor of safety of 1.5. This will allow us to accelerate and maneuver around aerially. Then it must provide 0.1195 newton meters of torque. This is for the ground component, and this will allow us to accelerate and maneuver around on the ground. Then it must transport the platform without the payload from the target position back to the starting position at least 100 meters, or under 100 meters. And then we must have more than one form of independent propulsion. So, from the propulsion subsystem, we derive two different components, the aerial and the terrestrial components. So, seeing here, we can see the aerial component and its associated elements. These consist of the aerial motors and proper combinations, seen here at the end of the propeller struts. And here is the terrestrial component with its associated elements. At the front, we have the two drive motors and wheels, and the back are caster wheels. So, once again, this is the aerial component. So for the driver, we selected the APC 18 by 5.5 inch diameter blades. We're getting 10 of these. So the first 8 are for the propellers, and then we have an extra set, so if any break, we can replace them. And the other 2 are for we can test them in failure to see where they're going to break, because we're testing these on the higher end of its factor of safety, and we want to know where it will start to fail. So for the aerial motor, we choose the Turnigy Helidrive SK3. We're going to be running this at 7,500 RPM max. So this is the terrestrial component. So for the terrestrial driver, we chose to mill out our own wheels on the front out of aluminum 6061. For the back, we chose to use caster wheels. This is so we can do differential front steering and it can turn freely. For the motor, we chose to use the Anaheim automation motor. This is courtesy of Dr. Gentilini, and we're going to each produce 0.0625 newton meters of torque. Now I'll hand it off to Wesley Stein to talk about the propulsion subsystem numerical validation.
Hello, I am Wesley Stein, and I'll be talking about the numerical validation of our propulsion subsystem. Now, the first set of requirements that we've got here deal with the range of our platform, which the propulsion subsystem is responsible for. It needs to travel between 50 and 100 meters initially to reach the target location. It needs to travel the same distance to come back, and it needs to be able to go up to 10 meters to get around any obstacles. Now, the principle or figure of merit that we're dealing with here is how much energy we can supply to the motors to reach the required range. And as you can see, the one that consumes by far the most battery capacity is our aerial motors that drive the propellers. They're expected to consume 7.73 amp hours. For comparison, the terrestrial component consumes 0.09. It's much less power. So obviously the aerial version has driven our power supplies, which is why there's exactly 4 batteries, 1 for each of the aerial motors. Now, we've designed this with a factor of safety of 2, which we meet, and we have, this is all based on a simulated mission, and we have enough energy to complete the full mission twice in ideal circumstances, which both those are factor of safety. The next set of requirements we deal with has the thrust that must be provided to lift our system with the propellers or aerial component. Early on in the design process, we decided we need a 150% thrust to weight ratio. This isn't only a factor of safety requirement, as the extra thrust beyond 100% is required simply to maneuver the quadcopter, because maneuvering involves running some of the motors at less than full capacity. We researched the topic and found out that 150% is the minimum to make a properly maneuverable quadcopter. Early on, we decided that our design weight would be 18 kilograms, and thus, in order to have the 150%, we have to produce 27 kilograms force of upward thrust with our 4 propellers, which is equal to 265 newtons. The third set of requirements here deals with the torque that must be produced by our ground wheels in order to maintain the proper acceleration at a grade of up to 2%. This would require, we've calculated a torque of 0.1195 newton meters. The provided torque is 0.1295, which fulfills that requirement also. And this table here simply shows the different requirements and how we have numerically validated them. We used a different kind of computer simulation for each of these, where we ran through a simulated mission and integrated the consumption of battery capacity and power, while also measuring the required thrust and torque in order to determine that we have numerically met all of these requirements. I will now introduce Abigail Kuto, who will be talking about our guidance, navigation, and control subsystem.
Thank you, Wesley. My name is Abigail Kuto, and I'll be discussing the Guidance, Navigation, and Control, or GNC subsystem. Joining me in the GNC subsystem is Damien Barraza and Christopher Klein. First, for the GNC subsystem definition. The requirements for the GNC subsystem are listed above. First, the subsystem shall navigate the platform to a point that is less than 2.75 meters from the specified position. Next, the GNC subsystem shall complete the mission using less than 16 amp hours of battery capacity. The subsystem shall limit the altitude of the platform to be less than 25 meters above ground level. Continuing on, the GNC subsystem shall navigate the platform around translational obstacles that are less than 10 meters in either length or height during the mission. And the last few requirements state that the GNC subsystem shall have more than one method of attitude determination and attitude control for the system. Pictured above is a CATIA rendering of all of the elements that comprise the GNC subsystem. The first component is the attitude determination component. There are 2 elements which serve as the 2 methods of attitude determination for the platform. The first is the directional sun sensor, which has an assembly of 5 solar cells mounted on top of the plate here. There's also an accelerometer mounted on the electronics board here. The second element, or the second method of attitude determination, is the inertial measurement unit, also located on the electronics board. For the attitude control component, there are also 2 elements which serve as the 2 methods for attitude control for the system. The first element is the airbase controller, which has 4 motors and propellers located on the ends of the propeller struts. The airbase controller element is used to control the attitude of the platform during flight. The second element is the ground-based controller, which has 2 motors on the ground, driving 2 gear systems, and 2 wheels. Controlling each motor independently enables us to use speed differential front-wheel drive to steer a platform to the target position and around obstacles. Lastly, the guidance component is responsible for navigating the platform to the target position where it will deliver the payload, and also navigating the platform around translational obstacles. The first element is the position sensor element, located here on the electronics board. which is responsible for determining the current position of the platform. Next is the obstacle detection sensor element, which has 4 sensors. The first is located on the front propeller strut facing forward. The next 2 are located on the left and right propeller struts, both facing outward. The placement of these sensors enables the platform to detect when it approaches an obstacle perpendicular to the front face, so it may turn and navigate parallel to that obstacle. Once it passes the obstacle, it can turn again and maneuver around the obstacle to continue to the target position. The last sensor of the obstacle detection element is located on the back propeller strut. It's facing downward, which enables us to detect when we've maneuvered over an obstacle. So we may continue the descent and continue to the target position. All of these elements comprise the 3 components of the guidance, navigation, and control subsystem. First, the attitude determination component has 2 elements, the inertial measurement unit and the directional sun sensor. The inertial measurement unit that we've chosen is the BMI 160, which has a 3-axis accelerometer and a 3-axis gyroscope. We'll also be using an external 3-axis magnetometer located on the sensor booster pack shown above. That magnetometer will give us a heading angle, which will be used to determine our attitude and help us to navigate throughout the mission. The second element of the attitude determination component is the directional sun sensor. We'll be using 5 Radio Shack solar cells on this assembly, which will give us a vector from the platform to the sun. And the second vector measurement will be the 3-axis accelerometer located on the electronics board. The accelerometer gives us a gravity vector downward. These 2 vector measurements give us the second method of attitude determination for the platform. Moving on to the attitude control component, there are 2 elements, the ground-based controller and the air-based controller. For the ground-based controller element, we've chosen to use the hardware already picked out by the propulsion subsystem as our actuators to steer the platform on the ground. That consists of the motors and the wheels shown above. For the air-based controller, again, for our actuators, we will be using the hardware chosen by the propulsion subsystem, the 4 motors and their propellers. And lastly, the guidance component has its 2 elements, the position sensor and the obstacle detection sensor elements. For the position sensor, we'll be using a GPS receiver, which gives us latitude, longitude, and altitude of the platform, therefore giving us a current position. We'll also be using the temperature and pressure sensor, which is included on the sensor booster pack with the IMU. This redundant measurement allows us to calculate the current altitude. So we will monitor how high we're going when we're trying to get over an obstacle. Lastly, for the obstacle detection sensor element, we have chosen to use 4 HCSR04 ultrasonic sensors, which can detect when an obstacle is up to 4 meters away, perpendicular to the face of the sensor. With that, I'd like to pass it on to Christopher Klein to discuss the GNC subsystem numerical validation.
Thank you, Abigail. My name is Christopher Klein. I'll be going over the GNC subsystem numerical validation. The design metric for requirement 1 is positional accuracy. The first element is the GPS position sensor. It has an accuracy of 2.5 meters. Next, the ground-based controller has a steady state error of 5.0 times 10 to the negative 14 meters. What this means is that according to our controller, the platform will get within that range plus or minus of the input location. We are trying to determine if this will be negligible, but this should satisfy our 2.75 meter requirement. The design metric for requirement 2 is battery capacity. The first element is the ground-based controller. It uses 0.011 amp hours, and the air-based controller, which uses 5.824 amp hours of capacity. This gives us a total of 5.835 amp hours. This is well below the requirement of 16 amp hours. Part of this gap comes from the factor of safety that was put on that 16 by propulsion. That was a factor of safety of 2. Also, our controllers do not yet model friction or drag, and assuming the platform is being operated manually, it will be less efficient and therefore require more battery capacity to be used. Requirement 3 has 2 design metrics. The first is altitude and the second is positional accuracy. For altitude, the element is the air-based controller. Our current simulation reaches a maximum altitude of 13.4 meters, and the altitude is limited to 20 meters. Once again, the positional accuracy is the GPS. It has an accuracy of 2.5 meters. When you combine the 20 and the 2.5, we get 22.5, therefore satisfying our 25-meter requirement. Requirements 4 and 5 have a design metric of distance. First element is the obstacle detection. These are the ultrasonic sensors. They will sense an obstacle when it is 4 meters away. We then have a stopping distance. This comes from our simulate controller of 0.71 meters. This will put us at 3.29 meters from the obstacle. Should give us plenty of room to turn. Numerically, the platform should turn with a turning radius of 0. However, we realize in actuality it will have small deviations. We will then start traveling 10 meters along the obstacle. We intend to measure this 10 meters using the IMU, which gives us an acceleration vector. Integrating this, we can get position. The error in the IMU, when you integrate it for position, will grow over time and distance. So we have not yet been able to numerically validate whether this will work or not, seeing as we do not yet have the IMU. The design metric for requirement 6 is the number of attitude measurements. The first element is the IMU, the inertial measurement unit. This gives us an acceleration vector, an angular velocity vector, and a heading angle. From this, we get one attitude measurement. We then have the directional sun sensor. This gives us a sun vector, as well as a gravity vector, giving us 2 attitude measurements, satisfying our more than one requirement. Requirement 7 has a design metric of number of actuator types. First is the ground-based controller, which has 2 separate wheels powered by 2 separate motors, giving us 1 type of actuator. Then the air-based controller, which has 4 propellers, all powered independently by 4 separate motors, supplying us with our other type of actuator. This gives us 2 types, satisfying our requirement that we have more than 1 type. Here you can see what requirements have been numerically validated. All but the distance requirement have been numerically validated. The reason for that being is we have not integrated all of our simulations together yet, so while we are able to numerically validate each maneuver, we cannot validate it as one continuous mission. And once again, the IMU being used to measure distance along 10 meters going along the obstacle has not been able to be validated yet. With that, I'll pass it to Brandon Clefman, who will go over the command subsystem.
Thank you, Christopher. My name is Brandon Clefman. I will be discussing the command subsystem. First, I would like to introduce William Hainsworth, the other member of my subsystem. I'll be going over the command subsystem definition. The requirements for our command subsystem, the first is that the communication range between the command subsystem and the ground station shall be less than and equal to 200 meters. The command subsystem shall communicate with the ground station at an update rate greater than or equal to 1 hertz, and the number of interface pins on the command subsystem shall be greater than or equal to 42. In addition to that, we have the command subsystem shall provide a nominal voltage of 22.2 volts, an instantaneous current supply greater than 321 amps, and a battery capacity greater than 16 amp hours. See, shown on the screen is the CATIA rendering of the command subsystem. I will point out some of the major components on the mock-up here. First, we have the battery system, which is located in the center in the blue. There will be 4 independent batteries which will be connected together in parallel. We also have the microcontroller unit, which is located directly in front of the batteries. That will perform all of the onboard computations for the system. Electronic speed controllers for the aerial motors are located on each of the struts before the propellers. And then lastly, we have the transceiver radio, which will be located above the batteries to get a better communication with the ground station. For the command subsystem, we derive 3 major components. First is the data handling component. Then we have the power component, and lastly, we have the ground station component. For the data handling component, we have derived 2 elements. We have the microcontroller element and the transceiver element. For the microcontroller element, we will be using the Texas Instruments TM4C evaluation board. This particular board has a 32-bit ARM microcontroller power unit. As for the transceiver element, we'll be using the 3D Robotics Radio version 1. This particular unit has been provided by Dr. Brian Davis in the computer engineering department. It has two components to it. The first is this one located here, which has the pins. That will be connected to the microcontroller through wires. The second is this USB part here, which will actually plug into a laptop and allow us to communicate to the laptop over serial interface. For the power component, we have derived two elements. We have the power control element and the power source element. For the power control element, the aerial motors, we will be using electronic speed controllers. Those are again located on each of the 4 propeller struts. For the ground motors, we will be using 4 half-H bridges. This will allow us to control the motors on the ground, which are actually brushed instead of brushless. As for the power source, we will be using 4 Turnigy 6-cell 20C 5,000 milliamp hour batteries. Again, these will be connected in parallel, giving us a total of 20 amp hours of battery capacity. For the ground station, we have derived 3 elements. We have the user interface element, the transceiver element, and the power element. We will be using a standard laptop such as this for our ground station. For our user interface, we have designed an initial user interface, shown in the top right. This is all of our status information, whether the platform is flying or driving, and which motors are currently operational. In addition, we have whether or not the vehicle is being driven manually or autonomously. Down in the bottom left, we have designed the buttons to allow us to connect from the PC to the radio, which will be plugged into the laptop. On the upper right, we have our information on the current location and the orientation of the platform in real time. This will give us the GPS position and altitude, as well as the roll, pitch, yaw of the platform during the mission. Lastly, on the bottom right, we have the sensor status from each of the 4 ultrasonic sensors. This will indicate whether an obstacle is being detected by each of the 4 sensors. Next, we have the transceiver element. Again, this is going to be the 3D Robotics Radio version 1, again provided by Dr. Brian Davis. The unit plugging into the laptop will be the piece with the USB. For the power of the ground station, we'll be using the laptop battery as well as a standard AC power supply if necessary. At this time, I would like to pass it to William Hainsworth to discuss the command subsystem numerical validation.
Thank you, Brandon. My name is William Hainsworth, and I'll be discussing the command subsystem numerical validation. For our first requirement, our design metric was the communication range. Our desired communication range was 200 meters. The radio that we have has a proven range of 1,000 meters, and we will be able to use that for our communication. Our second requirement is our design metric was the update frequency and data rate that we would need to communicate between our platform and communication. The packet size that we expect is 127 bytes, which is equivalent to 1,016 bits, and we have a 1 hertz data rate that we are desiring. So a desired total bit rate of 1,016 bits per second is required. The radio that we've chosen has a capacity of 250,000 bits per second. For our third requirement, we have a design metric for the number of interface pins. These interface pins are responsible for the communication between all of our connected components, such as the motors and sensors. So our desired for that is 42 pins, and the microcontroller that we've selected has 80 pins. For our fourth requirement, the design metric is the nominal voltage that we desire. So for that, we need 22.2 volts is the desired voltage to operate our motors, and the nominal voltage of the batteries we have selected is 22.2 volts. For our fifth requirement, the design metric is the instantaneous current that will be available to all of our connected components on our platform. The desired instantaneous current is 321 amps. This is if we are running all of the components at maximum power during the operation of our mission. The actual instantaneous current supplied by the 4 batteries that we have selected is 400 amps. For our sixth requirement, our design metric is the battery capacity. The 4 batteries that we have selected are going to be in parallel and will produce an actual battery capacity of 20 amp hours with a desired capacity of 16 amp hours. Above is the table that shows the validation methods we selected and whether or not we numerically validated each of our requirements. And as you can see, we numerically validated all of them. At this time, I would like to turn it over to Kaylin Kubner to talk about the structured subsystem.
Thank you, William. My name is Kaylin Hubner, and I'll be the first member to talk about the structure subsystem. With me on my team is Corinne Rotabot, team lead, and Jessica Chow. and I'll be discussing the definition. Here are the requirements listed above. The structure subsystem shall support a mass that is less than 18 kilograms. It shall support a thrust that is less than 27 kilograms force. It shall support a torque that is less than 20 kilogram centimeters, and it shall deploy a payload that is greater than 5 kilograms. Here is an overview of our system. It's a CATIA model above. I'll be referring to the mock-up. So we have our plate, we have a battery and solar panel cage, we got a rear front wheel chassis, and then the 4 propeller struts. On the underside of our propeller struts, we have a stringer and the ultrasonic sensor brackets. Underneath our plate, which is hard to see on our mock-up, we have the payload deployment system. We'll have 2 solenoids. Each will have a payload strut that it will sit on. On the solenoids is going to be a solenoid bar, which is going to extend into our payload bay, which will house our payload. Our structure subsystem is divided into 3 components: the body, the payload, and the payload bay. For the body, we'll be utilizing 2 different materials. For the plate and the propeller struts, we'll be using 0-90-degree bidirectional carbon fiber, which is provided by Dr. Lanning. And then for the battery cage, the chassis, and the stringers, we'll be using 60-61 aluminum. For a payload, we'll be using 2 steel cylinders, which will be provided by Embry-Riddle Aeronautical University's machine shop. For the payload bay, we have 2 elements, the storage and the deployment. For the deployment, we'll be using 2 solenoids, which we purchased by Delta Controls. The maximum stroke of these solenoids is 1 inch, and at 1 inch, it produces a pull force of 18 newtons, which is the minimum force that these solenoids will produce. And for the storage, we'll be using a plastic Rubbermaid Tupperware, which will be provided by Kernova. Now I will pass it on to Jessica Chow to talk about the structure, subsystem, numerical validation.
Thank you, Kaylin. My name is Jessica Chow, and I will be going over the structure subsystem numerical validation. For our first requirement, the design metric is maximum platform mass. Our aerial propulsion system can lift a maximum of 18 kilograms, so our platform must weigh less than this. Currently, it weighs 17.664 kilograms, therefore validating this requirement. Our second requirement has a design metric of maximum stress. The components for the aerial system, which include the aerial propulsion strut and the plate, are made out of carbon fiber, which has a maximum yield stress of 500 megapascals. The maximum stress encountered in both of these elements is 218 and 317 megapascals respectively, which is lower than the 500 allowable yield strength in these propulsion elements. Therefore, we have met this design requirement. For our third requirement, the design metric is also maximum stress, but this time in the aluminum parts of the terrestrial component. The allowable yield stress of aluminum is 95 megapascals, and the maximum stress encountered in these elements is 39.4 and 53.8 megapascals respectively. Therefore, we meet this design requirement. For our last requirement, we must deploy a payload with a mass that is greater than 5 kilograms. Currently, the payload that we're using is 5.035 kilograms. Therefore, it is larger than 5 kilograms and validating our design requirement. As you can see from the table above, out of the 4 requirements we have numerically validated each of these. I would now like to pass it off to Joseph Prosper, who will discuss our system numerical validation.
Thank you, Jessica. My name is Joseph Prosper, and I'll be going over the system numerical validation. I'll begin by covering the system requirements. The first 2 requirements is that the system shall deliver and deploy a payload with a mass that is greater than 5 kilograms. The system shall transport a payload over a distance that is greater than 50 meters but less than 100 meters. The system shall transport a payload to a position that is no farther than 2.75 meters away from a target position. This is our accuracy when dropping off the payload. The system shall travel over a distance that is no greater than 100 meters from the target position from the to the starting position without the payload. The system shall maintain an altitude that is less than 25 meters during the mission. The system shall have more than one form of independent propulsion and more than one method of attitude determination and attitude control. The system shall travel around translational obstacles that are less than 10 meters in the horizontal direction and the vertical direction. So if the system comes upon a wall that is less than 10 meters in the horizontal direction, it will drive around it. And if it comes across a obstacle that is more than 10 meters in the horizontal direction, it should be able to fly over it. The system shall have a mass that is less than 18 kilograms, and the system shall not operate if the amount of precipitation for the current day will be greater than 0 inches. So our mission envelope is that there is no rain or snow that day. All right, above me you will see a chart that says which system requirement relates to which subsystem. So for instance, the first requirement, the payload mass, will be validated by the structures and propulsion subsystem. And here are the requirements 10 through 14. On the chart above me, you will see the primary system objectives on the left, the system requirement that satisfies that objective, and whether or not it has been numerically validated on the right. These primary system objectives, to restate, are required for the mission to be a success. And we have numerically validated every single one of these objectives except for the 9th, which must be experimentally validated. Here are the secondary system objectives. We have not numerically validated the first and second because we are still working on getting those simulations together, which encompass both the terrestrial and the air-based components together. As a reminder, these secondary systems objectives are desired but not necessarily required to successfully complete the mission. Finally, once again, the first tertiary objective is not numerically validated, once again, for the same reasons. We have not put the simulation together. All right, I would like to pass it back to Estelle Fortes to talk about programmatics.
Thank you, Joseph. Again, I'm Estelle Fortes, and I will be discussing the programmatics. Here is the team's labor hours, organized by category. As of today, the team has worked a total of 2,506 hours. Here is our project budget, organized by subsystem. That includes a 15% margin. At this point in our design, we have $145 remaining of our $1,500 budget allocated to us by the College of Engineering. Now I will discuss the summary and conclusions. In this presentation, we went over our mission concept, our system definition. We talked about each of our subsystems and their numerical validation, then moved into our system numerical validation and programmatics. In conclusion, all of our primary system objectives have been numerically satisfied. 1 of 3 of our secondary system objectives have been numerically validated, and neither of our 2 tertiary system objectives have been validated. And as Joseph mentioned, although we have not fully numerically validated our secondary and tertiary objectives, we will be able to complete a successful mission because we have numerically validated our primary system objectives. Now moving to lessons learned, Ouranos has learned many things over the course of this semester. Some are listed above, most notably that duct tape will remove carbon fiber splinters. Ouranos would like to acknowledge the following individuals for their advisement and assistance in the development of APOPHIS. This concludes our presentation. We would like to thank the panel for their time. Thank you.
To start off, I just want to say that was a pretty good presentation, and this is actually making me want to come back for the detail semester, see how it all worked out.
Thank you.
So, yeah, I have a couple questions for the structures team. For your mass, do you have any mass allocated for unexpected equipment that may be added on? Because one thing I've learned is that no matter what you set for mass, there's always weight that's being added.
I'll defer this to Corinne Rodabaugh.
Thank you. We have not actually allocated that much, but at the current time, all we are really missing is our wires, which we estimate to be about 100 grams, which will put us at about 17.75. And that's including, our estimated weight up here is based off the CATIA model. I estimated all the densities that went in, And also the screws are longer than they're gonna need to be, so that will take off some weight. We have quite a few screws. So hopefully it will be lighter, but we will probably need to take into account the unexpected masses. Thank you.
Okay, and for system requirements on slide 109, it said the system shall deliver a payload with a mass that is greater than 5 kilograms. So if I wanted to throw something on there that was 200 kilograms, would it still fly?
No.
So just for future, if there is a max, put it on there, because there are those engineers out there that have tried to throw that curveball and saying, okay, let's just put as much weight as we can on there, see if we can lift it. So,
Okay, thank you.
good job, Steph.
Hello. All right, so I have several questions. Well, good job, by the way. You had a really smooth transition, so very clean. I like that. I think first one, it was more of a suggestion. At the beginning, I couldn't figure out whether it was fully autonomous until the very end of the slide. So it'll help if you add it at the beginning in the objective. My question will be on slide 12. Yes, so for this setup, what inspired this?
So this animation was to show the 2 variations of obstacles that we'll be able to maneuver around. And of course this is to scale, so what we wanted to show was essentially, I'll defer this question to Corinne.
Okay, so part of our customer's request was we are able to drive around an obstacle that is less than 10 meters in length, or fly over an obstacle that is less than 10 meters in height. So we basically decided to do this. We're going to put up 2 obstacles and make sure it can go around both. This is just the base I set up. Each obstacle is 25 meters from the starting location. The target location is 25 meters after the long obstacle. This may not be the final setup for our testing, but this is one example of what we could do.
Okay, thank you. Was there any practical reason that inspired this? Was it a defense reason or just an experiment?
I think it was just experiment.
Thank you. Next question is on slide 43. For slide 43, for the last one, it says have more than one method of attitude control. So it seems pretty vague to me. So where is this requirement coming from?
Abigail. So this was a system requirement initially defined by the customer. The 2 most notable ones were to have more than one method of attitude determination and more than one method of attitude control. I think the customer wanted to see where we would take this, and the way we decided to approach it is to have both a ground and air-based system, which comprises both of our methods of attitude control. And then on a side note, the second method of attitude determination is more of an experimental method. Obviously, we're using the inertial measurement unit as the primary method to determine attitude and to complete the mission. The second method, the directional sun sensor, the most notable difference is that it doesn't update as frequently as the IMU, probably won't be as accurate as the IMU, but it will serve as another method just to meet that system level requirement.
Okay, thank you. Just out of curiosity, who's your customer?
Dr. Benavides.
The last thing I want to focus on, because I'm an instrumentation and data engineer, so I want to ask a lot of questions about sensors and data processing. First one is, have you ever thought of using thermocouples? And I didn't see anything mentioning the thermocouples. And if not, why didn't? Did it ever come across your mind?
Can I clarify the question? Thermocouples for use of?
To test, make sure the battery or something is not overheating.
Okay.
At this time, we have not looked into that yet. It's definitely something we'll need to do when we do the experiment. And thanks for the input.
Yeah, that's something I think we need to find a detail design, just in case. Yeah, the other thing, I don't know how in depth you guys have looked into it. How I saw you have so many different sensors. How are you thinking of extracting all of those signals and time sync them? Make sure you're getting a real-time analysis or at the same time for all the buses. Have you thought of that, or is something you're looking into?
Yeah, so for, depending on the sensor, I'm sure they will, obviously some of them will operate at different frequencies. For example, the IMU, I believe, had a 10,000 hertz maximum operation for the accelerometer. We probably won't need to use it that fast, but we will be able to. Now the IMU will be beneficial for our attitude determination when we're flying, so having a faster one would be great if we can. But we're mainly going to be limited, I think, on the processing speed of the microcontroller, which is 120 megahertz. We will prioritize doing as much as we can with that processor and using it to its full extent, and not less than that. That way we can take advantage of all of the sensor information we can get. So the other systems may operate a little bit slower, like the accelerometer and the sun sensor, but because they will be used mainly as a secondary and for ground, it may not be an issue. But for the IMU, we will be trying to run as fast as we can. Same with the GPS system.
Okay, I think the question I was trying to get into was more for when you do your flight test, when you do your test. So how are you're going to look at the data. How are you making sure all of the accelerations and the sun sensor and all the information is synced to the same time? Have you ever thought of doing that?
At the moment, we have not looked into it.
Okay. Yeah, it's just something to more detail. I'm not sure to what extent you guys are going to do, but I'm very interested to see it next semester. Thank you. Good job.
Very nice project. This is a robotics project, so I'm very proud of you. I'm also very proud of your CATIA work. Couple of questions. First, you speak about 321 ampere multiplied by 20 volt. This is 6 kilowatt of power, basically 2 volts. Now, you have about 30 kilogram of mass, so it's 300 Newton of force. So that means that you are planning to go at perhaps a takeoff velocity of 20 meters per second, so 60 foot per second. Can you comment on these numbers?
Eli, can you answer your question?
So although we're planning on having an electronic capability of that, those amperages, for the actual running of the system, it will be at a much lower level going in.
Yeah, because the other question I have, you have 4 of these batteries in parallel. There's a lot of energy stored there. And so it could be potentially very dangerous. And so you may want to embed in your electric the schematic some elements to protect user and the systems from shorting that could be potentially be. I mean, if you short these kind of batteries, it will be explosion. So you may want to think about that. And the other question is on the carbon fiber. You have decided how to orient the carbon fiber. So you said it's 2 direction for the carbon fiber, 90 degrees.
Yes.
And decide optimize the direction for the fibers.
Yes. We chose a carbon fiber based on its availability. It's in the machine shop, and we are available to use it at no cost.
Okay. Well, very good job.
Thank you.
So let's see. I say this probably every one of these I go to, but I've been involved in lots of design crews at very major contractors building satellite programs and systems. And they spend millions of dollars on their design reviews, and many of them are not as good as what I can see today. So I just want to say that you guys do a really good job. School instructors here prepare you for a very good opportunity to succeed and excel when you move to industry and some contractors like these guys have done to North Grumman, which I've dealt with many times. So just want to say that I think you guys did a very, very good job with the presentation overall.
Thank you.
And I'm very anxious to come back next year and see how you do this design, which from my perspective is a very ambitious project at this level of class, if you will. In general, I just want to say that there was a couple of things. Very ambitious project. The design margins that I saw in a lot of cases were very tight from my perspective. That would mean to me that you're very confident in your analytical methods. If you're not all that confident, you might want to look at some of the margins, because specifically the wings that are holding the motors, whether or not that motor is going to cause the wing to dip or bounce or essentially vibrate. That can cause you certainly command and control kinds of problems. The other thing that I wanted to mention was I saw no discussion at all of the software or the command and control programming that's going to be involved with this, which to me seems like it's going to be quite complicated. So if you have not started looking into that, that's something that you need to get on right away, because that can be previous lecture that we were just at, that turned out to be a very distinct problem with them. They did not have enough time to get all the software properly working. So that's something that, on something like this, you need to get on right away.
Just to echo their thoughts. It's a good presentation. Pretty well rounded. You guys thought about most of the stuff, although I'm going to echo his thoughts on you guys are going to need to look into the software, but we'll get to that one. First thing, slide 11, please. That was a cool animation. It made things make more sense, so that wasn't bad. Slide 12, please. Another cool animation. The dot was really small and hard to see, and I was close to the screen. So just throwing that out there, it would be a little nice if it was a little bigger. Let's see, slide 16, please. So casters, as we heard from the last presentation, are kind of finicky. So the thing I was going to ask is this meant to, when it operates terrestrially, is it operating on smooth ground?
No.
You may want to reconsider casters then, because they don't go on much else other than smooth ground. Slide 28 is actually kind of a safety concern for me. APC propellers, I'm assuming those are the ceramic ones, right?
They're using according to the website, a proprietary composite blended fibers.
Mm-hmm.
I forget the term right now.
So do you have experience with that ceramic? So the reason I ask is because it is extremely strong. And if you're working with a really strong motor, whatever that propeller hits is probably going to break, not the propeller. So I just say that as a word of advice. You may want to consider wooden propellers, because whatever those hit, the propeller will break. Propellers are relatively cheap, and like if it's say a person, they won't get destroyed by the propeller. I just say that because we had an aircraft with a carbon fiber sandwich fuselage, and we used one of those propellers on a powerful motor, and it went right through the fuselage. Propeller's fine. So I just say that as a warning. If you're going to have exposed propellers, those things can do some damage if they hit something. And it's kind of your fingers. Oh, your fingers come off, no problem. So I just say that because if you're going to have exposed blades, those will be dangerous. Slide 31. The other wheels, do they have to be custom?
I'll let Wesley Stein answer.
Originally, when searching for wheels to meet this requirement with, we looked at plastic wheels, ultimately decided that they would not have enough traction and also maybe too weak when landing, because when this lands, it's going to put a lot more stress on the wheels than simply during driving. And so it has to be able to withstand that, and it also has to be light. We can't make it out of solid aluminum, it would be too heavy to fly. And so for that reason, we designed these custom wheels. They'll be machined out of a solid piece of aluminum in order to have lightning holes and be mostly hollowed in the inside, so as to allow us to have a strong wheel that can withstand the forces of landing while still being light enough for the aircraft.
Okay. Are you guys, one of you guys machining these wheels?
No, our in-house machinist, Patrick David, is going to machine them.
Okay, because I was just looking at it and thinking, these probably are not going to be cheap. So I was going to suggest, as a cost reduction, maybe continue to search for something that you can get off the shelf, but if Patrick is machining it, that probably helps with your cost a whole lot. He's a good machinist, though, it'd be nice to him. Let's see, slide 43, please. Okay, so this was kind of touched on earlier. From what I'm getting from this slide, you're going to need a lot of components, and they're all going to need to work together. I wanted to point this out as a warning that that can be dangerous for next year if you want to keep your sanity and sleep occasionally, because integrating parts takes forever, especially when software is involved. When I did it, we had I think 1 or 2 guys that were just constantly going, but they managed to do it. They didn't. Yeah, they didn't sleep much though. So I look at this and it just kind of puts off alarm bells to me, because I think this will be a real challenge to get these integrated from the software side. I think the hardware integration will be too bad. It's just, I think that's a big challenge. So I just hope you guys are up to it if that's what you're committing to. But that said, while I do think it's ambitious, I think it can be done. It's just understand what you're getting into. Slide 44. This is, I think, a slight misunderstanding on my part. I can't remember who was presenting this part, but whoever was doing it, okay, did you say it turned?
Steer, yes.
Okay, so does the quadcopter physically turn, or does it just translate?
It translates and it turns. It uses a speed differential front wheel drive, so operating the motors at the same speed will allow forward movement, operating them both backward movement.
Okay, that's what I was asking. I thought you were talking about in flight. I was just wondering, how would you turn in flight? So, I apologize for that. All right, and lastly, slide 125. Bullet number 2, that's an important one. Don't just communicate with your customer, communicate with them constantly, because what they need may change. You may run into something that maybe they didn't think about, or you think their requirements are unreasonable as a result. So that is a very important one. I just wanted to comment on that because that's a fun one I deal with occasionally, is customer decides, I don't want this, or I want this, and it's like, you haven't given me enough money to do that. So, yeah. But anyways, overall, good presentation. I look forward to seeing what you guys come up with next year, and I hope you succeed with it.
Thank you.